thanks to each of you for joining us today. And special thanks to MountainTrue for all it does up here with our preserving our Western North Carolina environment. I suspect I'm preaching to the choir, but I'll say it anyway. MountainTrue's broad range of activities deserve and need our continuing support of each of us. This talk is, of course, about regional geology, but I am going to take just a couple of minutes to introduce the book from which much of it has arisen. Whence These Special Places, I think of as a situation in which curiosity kind of got out of control. My initial curiosity was about how the area of unusually high valleys around Cashers and Highlands, known as the Highlands-Cashers Plateau, came to be. I spent some time Googling and Wikipediaing and quickly realized that I wasn't going to find the answer that way. In fact, it's something that had never been addressed, at least in writing. So I kept digging around deeper. My interest got broader as I went along, and eventually I find myself writing this book. Katie, I do resist being termed a geologist. I guess I will go with my retirement gig having been becoming a pop geologist. But it has been a very satisfying retirement gig. The book, true to its original impetus and my original curiosity and its subtitle, there's a focus on the Highlands-Cashers area, but it's not exclusive, and much of the material in the book does apply much more broadly. I think of it as three books in one. It's a description, an explanation of the geologic processes that have created the Eastern Blue Ridge. And by that, I'm referring to the eastern half to a third of the Appalachians that stretch from North Georgia across North Carolina and on up into Virginia. Certainly includes Asheville and the Blue Ridge Parkway for a number of miles in each direction from Asheville. The second role that the book plays is as a guidebook to a number of our well-known, typically, but noteworthy waterfalls and mountains. But it's a guidebook that's not just describing them, but exploring the geology that has created them and why they look the way they do. Thirdly, I wanted to capitalize on the photography to provide something that is be comfortable on coffee tables. So it's in a large format, premium paper, and it's offset printed in order to get the color quality that I wanted. Now the book provides a much richer, deeper, broader discussion than I can do in the next 25 or 30 minutes. So I'm going to focus in on a topic that I found particularly interesting, and that is, how do features in today's landscape reflect the effects of hundreds of millions of years of their geologic history? What is it in that geologic history that has produced what we see today? Now, I'm sure we're all familiar with many special and photogenic sites in our area. And you probably realize that a number of those waterfalls and mountains can be pretty different. They can look pretty different from others. Hey, let's see, I am having I'm having a technical issue here. I'm going to go off of screen share for just a moment and get this restarted. That should be it. Okay. Back to screen share.
There, we're seeing your PowerPoint now.
Yeah. Okay. There we go. I'm sure we're all aware of differences that we see. For example, mountains like Looking Glass, smoothly rounded. Just 5 miles away, Devil's Courthouse, quite a different character to this mountain, very rough and uneven. Or the pointy, jaggy, craggy nature of Craggy Pinnacle, which again, very different from what you see at something like a Looking Glass. Waterfalls, sliding rock, it's a waterfall that's smooth enough that at least a lot of people younger than me are very comfortable sliding on. On the other hand, 2 miles downstream from Sliding Rock, you find this, Looking Glass Falls. Very, of course, a large, abrupt drop with very angular sort of walls and lots of layering and craggy stuff. So these contrasts are really reflective of the fact that we in this region have two basic families of rocks. Those two families of rocks have radically different geological histories, and therefore they have very different characteristics that interact with the forces of erosion and weathering in the modern environment to provide very different types of features that we see. To get a handle on this, we're going to have to spend some time talking about geologic history. About 550 million years worth, which I'll be trying to compress into 5 to 10 minutes. I think that while very compressed, will be sufficient to help you appreciate how the differences in history are reflected in what we see today in our mountains and waterfalls. So let's start with the country rock, as it's called, the first family. Called the country rock because it was here first. It's the rock into which the second family, which we call the plutons, and I'll explain that in a bit, intruded. Where did our country rock come from? Well, it dates back about 550 million years in very round numbers. It didn't form up here. It actually didn't even form on dry land. It formed at the bottom of an ocean. That ocean was called the Iapetus Ocean, but you can think of it as analogous to the modern Atlantic. It was off the coast of the landmass that has become North America. Off that landmass, there were rivers that were carrying massive quantities of sediments and laying them down in layers on that in that ocean. Those sediments were quite varied. There was silt. There were very fine muds. There were various grades of sand. And also contributing to the mix was an arc of volcanoes off the coast that were adding lava and ash into these sediments that were accumulating. As they accumulated miles thick, water squeezed out, minerals that were dissolved in the remaining moisture would precipitate and cement these sediments into rocks. Sedimentary rocks, so called, because they're exactly the same sediments that were deposited in that ocean, just cemented together as rocks. Now, obviously, there is a tremendous amount of work that has to be done to move those types of rocks, which are not what we see at the surface today, up to where they are today, ranging in elevation up to the top of Mount Mitchell, 6,700 feet or so. That work was performed by plate tectonics. That is the whole phenomenon of the Earth's outer rigid core, outer rigid surface, being divided into plates that can move around relative to each other. They're moving on a lower layer, not so rigid layer of the Earth. As they do, they can kind of slide along each other, like on the San Andreas Fault. They can pull apart, or they can crash into each other. And certainly underway by 500 million years ago, the plates that were in that ocean and that were on the other side of that ocean were headed towards and crashing into the plate that contained what is today North America. As they did fairly early in the process, and it shows here kind of this foot of this volcanic arc, sediments, the rocks that were on that ocean floor were scraped up like a continent-sized bulldozer blade, pushed up onto the continent, and then buried very deeply as a huge range of mountains was formed, rocky scale of the Rockies, burying these rocks that we see at the surface today 10 miles and more down. At those kind of depths, the temperatures and pressures are such that those rocks are transformed. The minerals reform themselves, they realign themselves. The rocks become different rocks. And those are the rocks that we see at the surface today. They're called metamorphic rocks. Often they feature interesting patterns of lines and swirls, reflective of the metamorphic process and a lot of the history that followed. The process of these plates converging into North America, as indicated by this arrow down here, continued for about 200 million years, until about 300 million years ago. Towards the end of that process, what is today Africa actually impacted and attached itself to what is today North America. As it did so, it built up a second range of mountains, this one Himalayan in scale. And perhaps more importantly to the future of our own rocks here, it detached and pushed 150, 200 miles or so to the northwest, a large slab of the Earth's surface. That moved the rocks that we see at the surface today into their location, current location relative to the North American continent. So that's a lot. The takeaway for our purposes is that the country rock was formed from a wide variety of sediments. They'd been layered and chaotically, in chaotic ways, mixed up. They were later subjected to lots of heat, pressure, pushing around for hundreds of millions of years. So if you were a rock formation with that kind of history, what would you expect your character to be? I would suggest that one thing you should expect is a lot of variety. Remember, lots of different types of sediments contributed to the mix, and they experienced a variety of metamorphic conditions and other pushing around, folding, twisting over the period of being transported. Indeed, the term that geologists give to these rocks is the ash metamorphic suite. And suite emphasizes that this is not just a single rock. It's a bunch of different types of rocks, but they share a common geologic history and a high degree of metamorphism. I think you should also expect that all that layering that occurred and the differences in composition would create lots of internal weaknesses that would translate into fractures that can go off in all kind of directions. particularly remembering that this stuff has been pushed around and subjected to lots of torment over the eons. You'd also expect, because these layers are getting folded up in the process, that they would jut out of the surface at all kind of different angles, and that they would erode at different rates because of the variety of that is inherent in the rock. So that's pretty much what we see. This is a road cut near the entrance to the Arboretum. I think the variety that's inherent in the ash metamorphic sort of jumps out at you, and just looking at all the colors and textures in that. I think it shows more dramatically, perhaps, in this image. I'll show you towards the end where this was taken. But every rock in this picture is part of our country rock. The black stuff sourced from the volcanoes. This tannish gray, think of that as having been a muddy sandstone, a mix of mud and sand. The lighter stuff derived from cleaner sands that formed into rocks. The whole thing bespeaks of the enormous pressure and that these rocks have experienced. The folding, the tilting, says a lot about the geologic history of their creation and eventual transport to where they're currently located. At the risk of being diverted, I'm going to briefly take you to the opposite extreme of those black rocks, to shining rock. It's a very unusual rock in the ash metamorphic, but we think it's part of it. Every rock in this picture is actually snow white, subject to a little bit of pinkish or reddish mineral staining. All the gray stuff is lichen or shadow. This thing stretches up Shining Rock Mountain, so you can trace it. Some of it's covered up with underbrush. You can trace it 1,500 feet or so, goes 70 to 100 feet high, composed exclusively of fine-grained quartz. Its uniqueness has led to a little research project that Dr. Brittany McNamee at UNCA and I have been working on and hope to publish this coming year, trying to sort out how something like this formed. I'll go ahead and give you my favorite hypothesis, which is that this was once a snow white beach on the shore of that ancient ocean. You can almost feel the palm trees swaying, but that doesn't work because palm trees hadn't been invented back then. You actually can find along the Gulf Coast today beaches that have sand of a similar size and purity that is reflected in shining rock. The layering shows up, for example, in this slide. You can see how this is tilted up at an angle and helps create a ragged, jagged surface at the top of this mountain. This is similar, but taken to an extreme. This is, in this case, and this is a trail. By the way, these rocks are sticking up about a foot. These are a couple of feet. The green thing is a glove I threw down in a rather unsuccessful attempt to provide some scale. Some of you may be familiar with this. Well, what has happened here is that these rock layers have just turned on their sides, and the weaker ones have eroded out, leaving these fins that are sticking up pretty much vertically. That's a clue to where this picture, where this is located. That's part of the tower structure at the top of, for the transmission tower at the top of Mount Pisgah. Revisit Craggy Pinnacle briefly, just to focus in a little more on its kind of pointed peak and the craggy, uneven, abrupt character of the mountainside. Look at some waterfalls, Pearson's Falls, for example. Layering is very obvious in this very rough and busy surface. The layering also gives us some rock slides. This one was on Town Mountain 5 or 6 years ago. You can see the original road cut here with these drill boreholes. The rock that was perched up here above that cut really didn't care to have lost its lower support, and eventually gave way. And when it did, it slid off, broke off along these downwardly sloping layers. You can see a lot of that actually in the along the parkway. All right, let's talk about the plutons for a minute. A pluton is magma that is formed up in the earth but doesn't make it to the surface. It's trapped underground. If it made it to the surface, it would be called, it'd become a volcano, possibly be called lava. Stuck underground, it's called plutons, named for Pluto, the lord of the underworld. This is a highly oversimplified concept of what a pluton might be like. The point here is that it forms from a homogeneous masses of magma. It doesn't have all the layering, it doesn't have, it's younger, it doesn't have as much pushing around and metamorphosis. So it has fewer internal weaknesses, less internal fracturing. But it does have to fracture. The reason it has to fracture is that as it has been brought to the surface, huge quantities of rock, overlying rock, have been eroded away, and it has expanded. That pressure relieved causes the expansion, and it has to, didn't expand a lot, but it doesn't have to expand a lot for rock to have to fracture to accommodate that fracturing, that expansion. So it, unlike the country rock, it doesn't have all these pre-existing weaknesses and layers and fracture planes. So it tends to accommodate the expansion fracturing with something called exfoliation, which is basically, think of onion skin layers popping off the outside of this pluton surface. As a result, plutons tend to weather a lot more smoothly. They have a tendency to create rounded surfaces and to retain the rock's original shape. They also have fewer deep fractures, so less water penetration. That's important because when water gets into a rock, environmental acids invade, go to work, life happens, soils form, roots intrude, water freezes and thaws. Whole thing breaks down a whole lot faster than it does if water is flowing off a smooth surface. What do this plutons translate into at the surface? This is a top of a mountain over near Cashers. You're not going to bowl on this, but the contrast with Mount Pisgah or Craggy Pinnacle is pretty clear. And you also see the contrast probably even better in something like Waterfalls down in Hickory Nut Gorge, or for that matter, Hickory Nut Falls on down in Chimney Rock Park. There are a number of these pluton falls in Panthertown Valley. If you've ever been over there, I'm sure you've seen some of them. These falls are actually in some ways very different from each other. This one, Granny Burrell, is only 25 feet or so high, fairly gentle slope. Wilderness Falls, on the other hand, 70 to 100, and just quite vertical. But they share a relatively smooth water flow that derives from their heritage as plutons with exfoliation type fracturing. And of course, you see it in, as we revisit Looking Glass Rock. This actually is, the technical term for this among geologists would be an exfoliation dome, reflecting how the importance in its shape and current character of the exfoliation fracturing process that is typical of plutonic masses of rock. So I hope that's enough to help you understand how radical differences in geologic history have created two different general classes of rock forms that show up in our mountains and waterfalls. I think it gets even more interesting when you start mixing them up. They start being combined in one exposure. My favorite example of that, and I think it's my favorite because it's where I first started connecting the dots on this type of on this line of thinking is at Schoolhouse Falls in Panthertown. If you've been to Panthertown, I'm sure you've seen Schoolhouse Falls. This stream, for about a half mile upstream from this falls, is just a fairly level, walkable, gentle mountain stream. There are a few rolls, but no major barriers. You get here, it drops off a bit, and then boom, vertical 15 feet, abrupt drop. Let's try to figure out what's going on here. First, go up above the falls, and you'll see that it's coming across a lip of smooth, unfractured pluton. And that is true actually for a half mile upstream. But once it gets to this point, something very different happens. You go down below the waterfall and you can see what that is. It's no longer in pluton. We have the waterfall wall is all country rock. And not only is it layered country rock, but those layers are tilted up out towards the waterfall. That's important because those tilted up layers can easily catch water in the cracks. And as water gets in there, it's weakening the rock. It freezes and thaws. Eventually, these plates start dropping off the bottom, and it creates this recess. You can actually walk under this quite comfortably. Okay, you say that makes sense, but why hadn't it kept going? It's in this easy to work through stuff. Why did it stop here? Well, the answer to that is that it hits another layer of pluton. Smooth, unfractured rock that the waterfall lands on and flows right off of. And this is actually a phenomenon that once I clued into it, I've identified on a number of streams along, of waterfalls occurring in between layers of pluton. And in streams that flow in contact areas between plutons and our country rock. And that suggests that there must be a contact here. And in fact, there is. Just to the left of that falls, you can see it. This is, the gray is pluton, sort of a horizontal surface. The dark vertical wall at the back of the wall of the waterfall is country rock. The contact line is right there. The age difference across that line is 100 million years. I'm going to close out by talking for a couple of minutes about how these mixture of rocks can show up in mountains themselves. This is one of my favorite scenes. It's from top of Satula Mountain near Highlands. It's not only a beautiful view, but it has a lot of wonderful geology. You've got two pair of mountains, one foreground, one in the middle background. In each case, one member of the pair is an exfoliation dome. Black Rock Mountain here in front, Rock Mountain near Cashers in the back. The other member of each pair is different. Take this one first, Chimney Top Mountain. It actually looks like it wants to be a exfoliation dome if you ignore the chimney. And in fact, this lower portion is pluton. But then there's the chimney. What's going on there? Well, that chimney is country rock. It's a cap that has not yet eroded away. A geologist would call it a roof pendant. Until that is eroded away, the peak of that mountain is going to be shaped by and follow the rules that apply to the weathering and erosion of the country rock, not the underlying pluton. This is Whiteside Mountain between Highlands and Cashers. Pluton, pretty obviously down here in the lower half, and then a large cap of country rock, adding these sharp ridges, the pointed peak, and a lot of verticality that shows up even better in this final slide. This is taken from the valley below the south face of Whiteside Mountain. By the way, if you hadn't been to Whiteside Mountain, put it on your list. There's about a 2-mile loop trail from the Forest Service parking lot that goes along this rim, which is 1,500 to 2,000 feet above the valley below. It's the valley of the upper reaches of the Chattooga River. Below the red line is the plutonic part of the mountain. And I think that's very obvious over here. Here it gets very vertical, but it's not precipitously so. It rounds into it. Above the red line, country rock. And you can see the ragged, the rough stuff, different parts of the rock eroding faster than others. You can make out layering, the precipitous verticality that you don't get with the pluton. And if you have any further doubts, remember that slide from earlier with the climber amidst a variety of country rock. The arrow points to where that was taken. So I'm going to finish with a moral. I guess in this day and time, every talk needs a moral, even if it's a geology talk. And my moral is this. In geology, as in so many other settings, diversity is a powerful creative force. Because we have two rock formations in our eastern Blue Ridge, we get a variety of different types of exposures of rocks and waterfalls, mountains and waterfalls, some expressing the characteristics of just one of those two families of rocks, but others where they play together, they create features that are not possible in any other way, like Schoolhouse Falls or Whiteside Mountain. So with that, I'm going to thank you all for your time and attention, and turn it back over to Katie to see if there are questions that are coming in that I could address.
Thank you so much, Bill. I think we can all agree we learned a lot about some of our favorite parts of Western North Carolina from that talk. If folks have questions, feel free to put them in that Q&A and I'll have Bill answer them. We'll give folks a second to type in their questions. Bill, we had one person comment that they really enjoyed your presentation and felt like it was a very concise explanation of something that's really complex. So,
thank you.
Sounds like some folks enjoyed it.
That's what I was trying to do.
I don't see any questions yet, so if people have questions.
Why don't I anticipate one and answer?
Sure.
A common question, and by the way, feel free to ask questions about general geology or about specific places that interest you, which I may or may not know about, or about the writing and publishing of the book. One of the common questions is, are these the oldest mountains in the world? And that is, at the risk of puncturing a balloon, the short answer is no. That is a sort of a concept that got started when geologists were first realizing the age, realizing that there had been very old mountains formed where we are located. Remember those mountain building events during the time that Africa was being pushed up against North America 300 to 450 million years ago or so. You look around the world, you don't find mountains 300 to 450 million years old. Ergo, we still have mountains, those must be the oldest mountains. The flaw in that thinking is that it kind of ignores the reason that there's no mountains around the world 300 to 450 million years ago. And that's because mountains are going to be eroded away in 50 to 100 million years, even the Himalayas. As that fact has become really soaked in, there's been a fair amount of attention in recent years to, what is the source of the mountains we see today? And there's become general agreement among geologists who care about such things that it is the product of a more recent episode of uplift, probably in the last 10 to 20 million years, that has affected all up and down the Appalachian Range. It's supported by lots of lines of evidence. I mean, one's as simple as look at a map. The French Broad River is very circuitous, snakes around. That isn't what happens when rivers erode down out of mountains. That forms when rivers are forming in lowlands. You can see that in the Mississippi, and you can see how, though, if those lowlands start rising back up, that river channel stays the same and creates gorges, but very circuitous ones, like you see at the Grand Canyon, but also along the French Broad and the Tuckasegee River up here. There are other lines of evidence and inquiry that have explored the erosion rates and have really been pinpointing on a 10 to 20 million year range for these mountains rejuvenating. Now, why they rejuvenated, there's no agreement on. It's accepted it's probably something going on deep in the mantle. It is not a case of continents colliding with each other. I think the hypothesis that makes the most sense to me is something called delamination. It reflects the fact that the Earth's crust is generally less dense than the stuff beneath it, and therefore it floats on that lower, less rigid material. But the Earth's crust has a very dense, often has a very dense lower layer created as rocks change as they are subjected to lots of pressure and heat. And the thought is, and there's some studies, seismological studies that support this, that a layer of the crust containing that really dense rock has separated, delaminated, dropped on down into the mantle, and that has left the upper part of the crust with a lower average density, which causes it to rise up higher, like an iceberg floating in an ocean. So that's an area that's getting a lot of attention. It's not, doesn't make for a real good Chamber of Commerce type story, but it seems to be what the Earth has really been doing.
Thanks, Bill. We had a couple questions come in while you were talking about that. The first one, someone asked where they can get the book. Oh,
I'm sorry. Thank you. The book is available around Asheville at Black Dome and the Visitor Center. It's available at shops on the around Cashers, Highlands, and Brevard, Silva. You can find on the website. It's also available on the website. The website is www.greatrockpress.com. And the website price is includes shipping, so the price works out the same either way. The $23 plus tax.
Great. Someone else asked if you knew where the East Tennessee limestone comes from. For example, the White Oak sinks in Great Smoky Mountains as an old limestone cave that has collapsed.
Yeah, good question. It's obviously different geology than we have here, and the rocks that are spread across Tennessee are the product of shallow inland seas, primarily back during the time that our rocks were forming up and and after they had been pushed up onto the North American continent. Those seas lasted for many tens of millions of years out there and laid down thick layers of sandstone, and often shallow seas also tend to produce limestone. That, by the way, shows up in Cage Cove. Cage Cove is surrounded by mountains, but it's a window where the stuff that was pushed by Africa out over our continent have been eroded through to show the rocks that came along earlier and that were initially covered up as our mountains were pushed up. Cage Cove is so rich. It was a rich little agricultural community precisely because instead of the stuff that we have in the rest of the mountains, it was had calcium-rich sedimentary rocks that produced the soils that made that a very rich by settler standards little agricultural community. The rocks on across Tennessee, the plateaus out there, all have that provenance from those inland seas. They kind of lifted up in the plateaus, but not twisted and turned and tilted like they are over in our part of the world.
Thanks, Bill. We have one more question so far in the vein of talking about the age of the mountains that asks, are the Smokies the same age as the Blue Ridge further east?
Yes, I mean, the Smokies are part of the same phenomenon, but they are different rocks in the Smokies than we have. Some of those rocks up along the Tennessee and North Carolina line, particularly farther north, are truly ancient. They go back over 1 billion years to an earlier period of assembly of an earlier supercontinent. The rocks that are in the Smokies areas typically formed more like 650 to 700 million years ago, when before the Iapetus Ocean was formed. That earlier supercontinent called Rodinia rifted apart, but it didn't do it all at once. It earlier on had a sort of unsuccessful rifting, but nonetheless created some deep basins off to the west. And those basins eventually filled with deep sediments that became the rocks that today are in the Smokies. So they are, I don't know whether you define the age of a mountain by the age when it became a mountain or by the age of the rocks. I'm inclined to think it's by the time when it became a mountain, in which case they would be the same age as the Eastern Blue Ridge.
Thanks. Those are all the questions that have come in so far. So if folks have other questions, feel free to drop them in. Otherwise, we'll wrap up. Or
feel free to, if you go to the website, greatrockpress.com, there's some links where you can send questions to me. I'll be happy to connect with you.
Great. And this webinar was recorded, and so I'll send out the recording to everyone who signed up by the end of the week if you know anyone who would have liked to have seen it but wasn't able to join. We had a clarification question about the age that just came in, Bill, that says, so the Smoky Mountain rock is older than the Blue Ridge rock?
Yes.
Great.
With one exception, and that's Toxaway. You're familiar with Toxaway Falls area and the escarpment in Gorges State Park. The Toxaway is actually a pluton that goes back to that over 1 billion years old. that sort of got caught up with the our country rock and transported to where it is now. But otherwise, the rocks out in the Smokies, except down in Cage Cove, which are younger, but the rocks up in the mountains are going to be somewhat older than the rocks we have here.
All right, since we don't have any other questions, we'll go ahead and wrap up. But thank you everyone so much for joining, and thanks to Bill for spending his time with us today.
Yeah, my pleasure. Thank you.